All right, I put this review packet together a few semesters ago. The section numbers here might be the same, they might be different, but be aware that they very possibly are different in the books that we're using now, okay? I will send out a document of topics that the final exam will be over, and if you want to study those topics, those section numbers will be correct on that document that I'm going to send out later this evening. But for now, I would like to just do some sample problems over known topics that you should study to be successful on this final exam this year. So the first one here is simplifying a difference quotient. And so you don't have to memorize the difference quotient, right? It's written in the problem. But we will need to simplify this difference quotient for different functions, right? So if you wanted to look up on the internet, right, how to complete this type of problem, the keywords are difference quotient, right? So we want to simplify f of x plus h minus f of x all over h. So here's our function. Here's our f of x. So I like to do this in pieces, all right? I like to first find f of x plus h, right, and kind of write it out. And so if this is f of x, the function with x plugged into it, this is needs to be the function with x plus h plugged into it. And so everywhere there's an x, we're going to replace it with x plus h. So if we were to draw the skeleton of this function, it would look like so, right? Parentheses squared plus 3 times parentheses plus 4. Inside those parentheses, we are going to substitute x plus h. Okay, everywhere there was an x in the original function, we need to replace with x plus h. So now I need to simplify this. All right, I need to square x plus h. I need to distribute the negative 3 and then add 4 to the result. So over here on the side, I'm going to go ahead and square x plus h, which means we need to do x plus h times x plus h. So I am going to FOIL this, right? First, outer, inner, last, and then the outer and the inner terms will add together. So we get x squared plus 2xh plus h squared, right? So after I square x plus h, I'm going to replace it with this quantity. And then what I'm going to do is I'm going to distribute the negative 3, right? So negative 3 times x, negative 3 times h, and then the plus 4 is brought down. So at this point, you kind of scan for like terms, because we could add like terms if we had any, but we don't have any. All right, so at this point, I'm going to form the difference quotient. So I want you to see that we have a function evaluated x plus h minus the original function f of x all over h, right? So I'm going to do f of x plus h here, and I'll go ahead and put it in parentheses so I can see the difference here. All right, so here's the first part of the difference quotient, f of x plus h. And then what I want to do is I want to subtract the function. Okay, so I'm going to put that in parentheses as well. The function is x squared minus 3x plus 4. So I need to make sure I'm putting the whole entire function, okay, in the second set of parentheses. And then we want to divide it all by h. So at this point, I need to simplify this, right? So I'm going to simplify first by dropping the first set of parentheses and distributing the negative throughout the second set of parentheses and drop those parentheses as well. So we're going to get x squared plus 2xh plus h squared minus 3x minus 3h plus 4 minus x squared plus 3x minus 4, and then that is all over h. So at this point you should see some like terms, okay, and things should start canceling out. So the first of which, x squared minus x squared, cancels. Positive 3x, negative 3x, cancels. Negative 4, positive 4, cancels, right? Now, we have 3 terms left. They don't cancel each other out, but they do all have a common factor. And that common factor is h. So on the next line, what I'm going to do is I'm going to go ahead and factor an h out of each of these 3 terms. So the h gets factored out. If I take h out of 2xh, I'm left with 2x. If I take an h out of h squared, I'm left with h. And if I take an h out of negative 3h, I'm left with negative 3. All right, so we have this fraction now. Now the h that we factored out will cancel with the h in the denominator. We can't cancel inside the parentheses. It has to be the one on the outside. So after we do that, we get a simplified form of the difference quotient, 2x plus h minus 3. Okay, and this would be the final answer. All right, so the final exam is multiple choice, and so you would go through the work and then find the correct response and mark it, okay? All right, so the next problem here is determining where a function increases or decreases. And this isn't meant to be difficult, all right? But I do want you to make sure when we talk about increasing and decreasing, we want an interval of x values. Okay, so make sure to use x values. It doesn't matter the y values. Okay, it doesn't matter that it increases to 1 or 2 or 99, right? What matters is where is the function increasing and where is it decreasing. So this function starts off increasing, right? And you can see that. So it's increasing basically until negative 2, right? And then the function starts to decrease, and it's decreasing basically to positive 2. And then it increases again, right, past 2. And so what we would do is we would write those in interval notation. So before negative 2, we want to make sure we're writing this in the correct order. So least to greatest. So the least number here of this interval where it's increasing is negative infinity to negative 2. Okay. Now at negative 2, right here where this function is changing, it's not increasing nor decreasing there, so we don't want to include it with a bracket. We want to make sure we use a parentheses there. Right? And then the other interval where it's increasing starts at 2 and then goes to infinity. So parentheses positive 2 to positive infinity. Those would be the intervals where the function is increasing. Right? Where is this function decreasing? Here in the middle. Okay, it's decreasing from negative 2 to 2. And so we want to use x values only. And we always want to use parentheses, right? Because it's not decreasing at negative 2. It's decreasing just past negative 2 there. Okay. So this isn't meant to be difficult, but you do need to make sure you're only using x values and you're identifying the correct intervals. Those intervals should be least to greatest, okay, least to greatest. All right, so the next one, find the max and min of a quadratic. So if you know, right, all quadratics, they either open up or down. And so if it opens up, the function will have a minimum. And if it opens down, the function will have a maximum. And so you're only going to have one, either a max or a min here. So here is a sample quadratic, right? Negative 3x squared plus 3x minus 2. This particular quadratic or parabola is going to open down. And we know that because the leading coefficient is negative, right? So I'm just going to draw a sample quadratic or parabola that's opening down, okay? And so what's the max or min value of this quadratic? Well, it occurs at the vertex, right? And the easiest way to find a vertex is to use the vertex formula. And that vertex formula is negative b over 2a, comma, f of negative b over 2a, right? Where the a and the b come from the coefficients here, right? So first, negative b over 2a, if I calculate that value, or let's go ahead and write it down here. A is negative 3, B is positive 3, and C is negative 2. Okay, so if we want to do negative b up top, we're going to get a negative 3 up top, and then 2 times negative 3 in the denominator. And so we're getting negative 3 divided by negative 6, which is 1/2, right? So now what we want to do is we want to find the function evaluated at 1/2, okay? So to find the y-coordinate here, we're just going to plug 1/2 into the function. So negative 3 times 1/2 squared plus 3 times 1/2 minus 2. And I am just going to plug this into my calculator. Let me get it here. Alright, so negative 3 times 1/2 squared plus 3 times 1/2 minus 2 gets us negative 1.25. Okay, let me just change this to a fraction, and we get negative 5/4. Right? So now we have a vertex. All right. Now I know the vertex is at 1/2, comma, negative 5/4. All right. So I kind of drew my parabola in the wrong quadrant because the vertex is actually about here, right? And it's opening down, okay? So what is the max or the min value of this quadratic, right? So when we answer the what, we don't want to answer with a point, right? The max, this function here is going to have a max. And what is that maximum value? It's the y-coordinate, right? The highest, the biggest value this function is going to give us is actually negative 5/4. Okay, so the max, not make, max is negative 5/4. Okay, so make sure you're answering that question with the y value only. Right? The x value is just where the max happens to occur. Right? All right, so here on the next page, okay, we have some factoring higher degree polynomials. All right, so let's go ahead and do that. This one says list all the possible rational roots. Okay, remember roots is synonymous with zeros, And so when we list all the possible rational zeros, that is the P over Q list. All right, so you are going to be expected to be able to do this. All right, so P is all the factors of the constant, right? And this constant is 9. So my possible P factors are 1, 3, and 9. Q are all the factors of the leading coefficient. So the factors are 1, 2, 3, and 6, right? And so we need to come up with all the possible P over Q. So I'm going to put 1 over all the Q's, and then I'm going to put 3 over all the Q's, and then I'm going to put 9 over all the Q's, all right? So 1 over all the Q's. Looks like so. If I put 3 over all the Q's, and then 9 over all the Q's, here. Right. So then what we want to do is we want to make sure we don't have any duplicates in our list. So if they, not the ones over 1, but anything else, if they reduce, we're going to cross them off. So the first thing that reduces 3 over 3 is the same as 1 over 1. Okay, so I'm going to cross that off. 3 over 6 reduces to 1/2. 9/3 reduces to 3. And 9/6 reduces to 3/2. Okay, so here's the entire list, right? Now you won't be inputting this list. The question is going to ask how many, right? How many possible unique rational zeros are there? Right. So it's not how many zeros does this function have, because it has the word possible, all right? So even though this is a 4th degree, we know this function has 4 zeros. The answer is not going to be 4 here. How many are possible? Okay? How many rational numbers are possible zeros? And so those are the ones that work and the ones that don't work. And the fact that they need to be unique means we don't need to be counting these duplicates. All right? So if I count up the number of zeros in this list, 2, 3, 4, 5, 6, 7, 8, I have 8 numbers, but I need to multiply that by 2 because we have positives and negatives of each of those values. So 8 times 2 gives us a total of 16 possible rational zeros. All right, so the question is going to have a list of numbers, and so if you need to be able to come up with a whole list, you need to be able to correctly cross off the duplicates, and then you need to be able to correctly count, right, how many are left. All right, the next example, I don't believe there is a question on this, especially this form, okay? Provide a complete factorization. This is writing all the imaginary zeros and the irrational zeros as factors. This one here in particular has 4 complex zeros, right? So I'm just going to factor it for you real quick, okay? It goes from x to the 4th to x squared to nothing. And so I know it's going to factor here x squared and x squared, right? And so now I need 2 numbers that multiply to 36 and add to 13. And those numbers would be 4 and 9. Okay, so I'm going to get positive 4 and positive 9. Now x squared plus 4 and x squared plus 9 does not factor, right? Because they're a sum of squares. They would factor if they were negative here, but they're not, right? So in order to find the zeros here, I'm going to take these factors and set it equal to 0. Right, just FYI, this is considered fully factored, or actually, yeah, fully factored, okay, over the rational numbers, if you will, because none of the factors factor any further. So most of the time we've stopped here at this point, right? But the complete factorization wants us to use i's in our factors, okay? So if I set each of the factors equal to 0, I'm going to subtract 4 from both sides. And I'm going to get x squared equals negative 4. Now to solve for x, I need to take the square root. And if you remember, the square root of a negative is I, right? The square root of 4 is 2. So we're going to get plus or minus 2i, all right? And then here, if I were to do the same thing, I'm going to subtract 9 from both sides and get x squared equals negative 9. Then square root both sides and get x equals plus or minus 3i, right? So this fourth degree polynomial has 4 zeros, but the 4 zeros happen to be all imaginary here. And what this question wants is it wants you to write all those zeros as factors, whether they're real or not, okay? So we have zeros, 2i, negative 2i, 3i, and negative 3i, okay? All imaginary. So if I were to write those zeros as factors, we're just going to do x minus the 0. So if 2i is a 0, x minus 2i is the factor, right? If negative 2i is a 0, x plus 2i is the factor. 3i is a 0, so x minus 3i is the factor. Negative 3i is a 0, so x plus 3i is the factor. This is what we call the complete factorization, right? But these factors, notice they have imaginary numbers, okay? So this is factored over the rational numbers. This is factored over, over the real numbers and the imaginary numbers, okay? Complete factorization. All right, this question here, the question on the final is not written like this, okay, because we actually didn't really do this problem. But the question is going to be stemming from what you do with imaginary zeros, okay? So I want you to notice what happened above. This x squared plus 4 had 2 zeros, okay, but they were both imaginary, and they ended up being 2i and negative 2i. We had conjugate zeros here, and the same thing happened with x squared plus 9. We had a complex number and its conjugate. So that's what's going to happen, okay? If your polynomial has integer coefficients, okay, and real coefficients, all your complex zeros will occur in in conjugate pairs, right? So I want you to be able to state what a conjugate is. Okay. So for example, if we had 1 plus 2i, the conjugate is going to be changing the sign of the middle of the imaginary term. Okay, so the conjugate of 1 plus 2i is 1 minus 2i. Right? We're just changing the imaginary term here. So if we had negative 1 minus 3i, the conjugate is going to leave the real part of the number alone and change the sign of the imaginary part. So we'll get negative 1 plus 3i. Right? So in this one, we had a 0, 3 plus 2i. And so what else is also a 0 of this polynomial is its conjugate 3 minus 2i. Okay? So just remember that imaginary zeros occur in conjugate pairs, okay? So let me write that down. Complex zeros occur in conjugate pairs. Okay, so you won't have to find a polynomial per se, but you will have to be able to state what the conjugate 0 is. Okay. All right, the next series of questions is over rational functions. And so when we talked about rational functions, we were interested in 4 things. Okay, we were interested in the vertical asymptotes, the horizontal asymptotes, the x-intercepts, and the y-intercepts. All right, and so the question will be phrased just like this. Okay, you're going to have a set of three fractions, 3 functions, and you're going to be asked questions about all 3. Okay, so the first question says, which function has no horizontal asymptote? And so you will need to be able to remember the rule about horizontal asymptotes. And so remember, horizontal asymptotes have 3 cases. All right, and so just to remind you, the first case is if n is less than m. The second case is if n equals m. And the third case is if n is greater than m. Right? And each of these cases, the horizontal asymptote is different. And so if n is less than m, right? Remember, n is the degree of the top, and m is the degree of the bottom, right? N degree of top, m is the degree of the bottom. And so if the top is less degree than the bottom, then we have a horizontal asymptote at y equals 0. Okay? If the top degree and the bottom degree are equal, then we have a horizontal asymptote at a ratio of those leading coefficients, right? So we have a sub n over b sub m. We're just going to write the coefficients over each other. And if the top is greater than the bottom, there is no horizontal asymptote, okay, but there is a slant asymptote or an oblique asymptote. Oblique asymptote at the quotient, okay, q of x, right? So we would actually have to use division in order to figure that out, okay? So let's look at these 3 functions here and apply these 3 cases. So in R's case, the top degree is a 1, right? Because 3x is understood to be 1. The bottom degree is also 1. So the degrees are equal, right? So if the degrees are equal, the horizontal asymptote is at a ratio of the coefficients. So the coefficient, the leading coefficient of the top is 3, and the leading coefficient of the bottom is 1. So I'm going to write down here, case 2, right? And we want to do the horizontal asymptote at 3 over 1, okay? And actually it's y equals 3 over 1, right? Or y equals 3, okay? We'll have a horizontal asymptote at 3. Moving on to t of x. The top degree here is 2, and the bottom degree is 4. So the top is less than the bottom, okay? So t has a case 1, in which case the horizontal asymptote is at 0. Okay, no questions asked, right? If the top is less than the bottom, it's at 0. Right? In G's case, the top degree is 4 and the bottom degree is 2, so the top is bigger than the bottom. And in that case, there is no horizontal asymptote. Okay, so horizontal asymptote here, we would write none. Right? But there is an oblique asymptote, and we do need to find it, and you will be expected to find an oblique asymptote on the final. Okay, so to answer this question, though, which function has no horizontal asymptote, quite simply, we would just put g of x. Okay, but let's go ahead and find this oblique asymptote. Okay, So I need to divide x to the fourth minus 1, which means I need placeholders for x cubed, x squared, and the x. And then minus 1 goes at the back there. Okay. So I'm going to divide that by x squared minus x. Now I have to use long division in this particular problem because synthetic division doesn't work, right? There's more than one zero here, right? You can only use synthetic division if your divisor is linear. Okay. So I'm going to first divide first term by first term. So if I divide x to the fourth by x squared, I get x to the second power. Okay, so I'm going to line that up here with the x squared. I like to keep all my x squared terms in a line. Okay, so then what I'm going to do is I'm going to multiply x squared times my divisor. So x squared times x squared is x to the fourth. X squared times negative x is negative x cubed. Right? I know it's been a minute, but we have to review this. So what's next here in this long division problem is we're going to subtract, okay, this quantity. And so I like to do it mentally. Okay, I'm not going to actually change these signs. I'm just going to do x to the fourth minus x to the fourth cancels. 0x cubed plus x cubed is a positive x cubed, right? And then, since there's nothing below the x squared x or the negative 1, I'm just going to copy the rest of the quotient down. Right? Not the quotient, the dividend. All right. So what we're going to do now is we're going to repeat the process. Okay, I'm going to divide first terms by first terms. So x cubed divided by x squared is x. That's the next part of the quotient. So even though this is just x, I'm going to make sure I put the positive sign there, okay, plus x. And then I'm going to distribute that positive x through my divisor. So x times x squared is x cubed. X times negative x is negative x squared. And then we need to subtract. Okay. X cubed minus x cubed cancels. 0x squared plus x squared is a positive x squared, and the rest of it gets copied down, right? So we have to go one more time because this is not the remainder. Remember, the remainder is 1 degree less. And so the fact that these are equal degree means we need to keep going, okay? So what is x squared divided by x squared? Okay, it's just 1, right? So I'm going to put a plus 1 here, right? So now I'm going to distribute the 1. I'm going to get x squared minus x. And then I'm going to subtract that quantity. X squared minus x squared cancels. 0x plus x is x. Okay. And then I bring the negative 1 down. This right here is the remainder because it's 1 degree less than the divisor. But remember, the oblique asymptote doesn't care what the remainder is. It just wants the quotient. Okay. So up here, I'm going to write a y equals, and I'm going to box this quotient off. Okay, this would be our oblique asymptote, x squared plus x plus 1. Okay. All right, so I know that took a lot of time, but it is important to go over. All right, so the next question asked is which function has no vertical asymptote? So remember, vertical asymptotes are when the denominator equals 0, but you have to make sure everything is factored first, okay? So 3x doesn't factor, x plus 4 is its own factor, so this one's ready to go, okay? X to the fourth plus 1 doesn't factor because it's a sum, all right? But on G's, this one will factor, okay? So first, x to the fourth minus 1. We can factor that to x squared minus 1 times x squared plus 1, right? And then the x squared minus 1 is another difference of squares. So I'm going to factor it again here, right? So x squared minus 1 factors to x plus 1, x minus 1. And then the x squared plus 1 doesn't factor anymore, so it's its own factor. Right? So there the numerator is factored. The denominator factors, but it's only 2 terms, right? So remember when it's 2 terms, we're going to group it and factor out our greatest common factor. And so the greatest common factor here is x, right? And so we will, if we take out an x, we're left with x minus 1, okay? So notice that the top and the bottom share a factor. They both have x minus 1 as a factor. So I want to cross it off, right? And when I actually answer questions about g, I'm going to use this reduced form here, right? All right, so which function has no vertical asymptote? We're still trying to go there, right? Let me zoom out. So if I were to take the denominators and set them equal to 0, that would help me find out, okay? So set the denominator equal to 0, the reduced denominator. So in R's case, right? If I set that denominator equal to 0, there's a solution, right? I could subtract 4 from both sides and get x equals -4. Well, that means -4 is a vertical asymptote. In T's case, if I take that denominator and set it equal to 0, the first thing I need to do is subtract 1 from both sides. So I get x to the 4th equals -1. Then I will take the 4th root, right? So remember, 4th roots work just like square roots. You can't have a 4th root of a negative number. You're going to end up with imaginary numbers. So this is going to have no solution, right? Which means that this one does not have any vertical asymptotes. Okay, so already I know T is one of those answers. But you want to make sure there's not 2 different functions that don't have vertical asymptotes. So I'm going to set g of x. Okay, the denominator of g of x equal to 0. Now in reduced form, the only thing left is x in the denominator. Right, so if I set x equal to 0, that is my vertical asymptote. Okay, so R has a vertical asymptote at -4. G has a vertical asymptote at 0. T doesn't have one. Okay, so the answer to this question would be t of x. Right? It's the only function that doesn't have a vertical asymptote. All right. Which functions have an x-intercept? All right, so remember when we found x-intercepts, we're going to let y equal to 0. So we're going to set these functions equal to 0. Okay, so I'm going to do them in columns, right? So if I set r of x equal to 0, I get this equation, 3x over x plus 4 equals 0. So the first thing I want to do to solve this equation is get rid of that denominator. So I'm going to multiply both sides by x plus 4, and I get 3x equals 0. Right? Divide both sides by 3, and I get x equals 0. Well, that's an intercept at 0. All right? So I already know r is one of my answers. Okay? Let's check t. All right? So if I take the t function and set it equal to 0 and solve, right, what's going to happen? We're going to get rid of that denominator first. So we're going to multiply both sides by x to the 4th plus 1. And so we get x squared equals 0. So if I square root both sides, I get x equals 0. Here's another intercept at 0. Okay, so t of x is also a solution. What about g? Okay, set that factored form equal to 0. Because it's going to be a little bit easier. All right, set the reduced one equal to 0. So first thing, I'm going to get rid of that fraction, multiply both sides by x, and I get x plus 1 times x squared plus 1 equals 0. Well, I have 2 factors equaling to 0, so I need to set both factors equal to 0 and solve. So if I set x plus 1 equal to 0, I'm going to get x equals -1 as a solution. If I set x squared plus 1 equal to 0, I'm going to get x squared equals -1. Okay, and if I square root this, we all know what's going to happen, right? The square root of -1 is imaginary. So this particular factor doesn't have a solution, and this one has an x-intercept at -1. So the question was, which functions have an x-intercept at 0? Okay, the first two, all right? So r of x and t of x. They both had x-intercepts at 0, right? All right, which functions doesn't have a y-intercept? Okay, functions, that's kind of bad English there, right? Apologize. Which function doesn't have a y-intercept, or which functions don't have a y-intercept, all right? But y-intercepts, we're going to let x equal 0 and see what happens, okay? So again, I'm going to do all three, all right? So in r of x, if I let x equal to 0, I get 3 times 0 divided by 0 plus 4. So 0 over 4 is 0. Okay. So the x-intercept here is 0. What about t? I'm going to get 0 squared over 0 to the 4th plus 1, which gives me 0 over 1. Right? Remember, this is the OK fraction, right? So the answer is 0. So this one has a y-intercept at 0. What about g? Okay, I'm going to go ahead and use the original here. It actually doesn't matter, but I can foresee what's going to be easier to calculate. All right, so if we do 0 to the 4th minus 1 over 0 squared minus 0, we're going to get -1 divided by 0. Right? We can't divide by 0. This is the NO fraction, right? So this does not exist. All right, so which function doesn't have a y-intercept? Okay, the only one that doesn't have one is g. All right, the first two did. R and t had y-intercepts, g didn't. Right, so make sure you're reviewing all those rational function topics. Okay, vertical asymptotes, horizontal asymptotes, x-intercepts, and y-intercepts. Right. All right, so here's where if we were in a live class, I'd ask for ideas about inverse functions, right? But I don't have you guys in class, all right? Sad face, truly, because this is weird, and I do miss you guys, all right? But show f and g are inverses. There's some things that we went over, all right, about inverse functions. And so instead of asking you to find an inverse function or asking you explicit things about inverses, they're going to be more general in nature, right? So first, when we went over inverse functions, we talked about the fact that they have to be one-to-one, okay? So inverse, let me just write it, okay? A function must be one-to-one in order to have an inverse. All right, so remember what it is to be one-to-one, right? It passes the horizontal line test, okay? So it has to pass both the vertical line test and the horizontal line test so that our function is an inverse, right? If it doesn't pass the horizontal line test, the inverse is not a function, right? If you actually graph it out, okay? So the next thing we talked about is that the domains and ranges swap. Right, so keep that in mind, right? That if we had f of x and it had domain set A and range set B, and then if we were to look at the inverse, right, the domains and ranges swap. So the inverse domain would be B and the inverse range would be A, right? Domains and ranges swap. Individual points swap. swap. All right, so if f of x had a point 1 comma negative 3, the inverse would have a point negative 3, 1, right? We remember those, okay? So the other thing, when we graphed inverse functions, and when we drew those graphs, remember we reflected over that diagonal line, okay? So we're going to reflect over y equals x. Right, remember that diagonal line that we always drew? Okay, and then we put our mirror board on top of that diagonal line. We were able to draw those inverse functions. So remember they reflect over y equals x. And then remember their compositions. Okay, so if I did f composed with f inverse, all the functionality should cancel. And you should be left with x, right? The x isn't going to cancel, but you know the addition and subtraction will cancel each other out. The multiplication and division will cancel each other out. The square root and the squares will cancel each other out, and you should just be left with x at the end, right? So remember their compositions simplify to x. All right. So I think that's pretty much all about inverse functions there. So just know it's going to be more, I don't know, it's not going to be an equation, okay? It's going to be more theoretic in those questions. All right, one of the biggest things we went over was domain. Okay, we were constantly finding the domain of a function. And so what I'd like to do is I'd like to find the domains here. All right, of f and of g. So here we have a square root. So we want to make sure this radicand is greater than or equal to 0. All right, so what I'm going to do is I'm going to take the radicand and I'm going to set up that inequality. So I'm kind of like removing the square root, and whatever's underneath here, I want to be greater than or equal to 0, okay, because the square root of 0 is 0. So if I add 1 to both sides, I get x is greater than or equal to 1. Okay, that's the domain. Now, if I wanted to write that as an interval, greater than or equal to 1, remember we're going to put 1 on the number line. It's equal, so we're going to use a bracket, and we're going to shade towards the right. Okay, so the interval here is 1 to infinity. So if I do the same thing, here, if I take the radicand out and set it greater than or equal to 0, I'm going to go ahead and move the 4 just to keep the x on the left. I'm going to get negative x is greater than or equal to negative 4, and then divide both sides by negative 1. Remember what happens when you divide an inequality by a negative. Okay, you have to switch the direction of the inequality. And negative 4 divided by negative 1 is positive 4. Okay. So again, if I wanted to write the interval here, we want numbers less than 4, which is to the left. And so my domain is going to be negative infinity to 4. Okay, and end with the bracket. All right, so what is all of this? Okay, f plus g, f minus g, f times g, and f divided by g. All right, we're just going to find the domains here. So what happens if I add these square roots? All right, not much. We're just going to take the two square roots and put a plus sign in between them. Okay, same thing with subtraction. Multiplication, we could multiply what's underneath. Division, we could divide what's underneath. But what's more important here is what the domain is going to be. All right, so I'm going to call this set A, and I'm going to call this set B. Right, so A is 1 to infinity, and B is negative infinity to 4. So what I want you to remember is that if we were to do f plus g, f minus g, or f times g, the domain is going to be the intersection of A and B, right? A intersect B, which means where does these sets overlap, right? So if I were to put both sets on the same number line, okay, 1 to infinity, I'm I'm going to graph it up top. And then negative infinity to 4, I'm going to graph that down below. The intersection is going to be where they overlap. And they're only going to overlap here in the middle, right? So the domain A intersect B in this case is just from 1 to 4, okay? So if we were to do the division, the domain is slightly different, right? So remember, what I want you to remember is that the domain is A intersect B and g of x can't equal 0. Okay, the bottom can't equal 0. So look at your radical here. What would make that equal to 0? 4 minus 4, right? So if I were to plug 4 in this radical, I get 0. The square root of 0 is 0, and I would be dividing by 0. So I don't want to put 4 into this fraction here when I do f divided by g. And so what we're going to do with the domain is, instead of including 4 with a bracket, we're going to put a parentheses, because we can put all the numbers up to 4 into this function, just not greater than 4. All right? So there's domains of radicals. And so what I'd like to do the same thing here, but have fraction functions. All right? So remember, with a fraction, you can't divide by 0. And so what we're going to do is we're going to take the denominator and set it equal to 0 and solve. Okay? The denominator can't equal 0. Right? So why don't you just take the denominator, set it not equal to 0. All right? So if I solve this, I'm going to add 2 to both sides, and I get 3x, okay, can't equal 2, and then divide by 3, which means x can't equal 2/3. Right? That's the domain. Right? X can't equal 2/3. If I did the same thing for g, it doesn't matter what the numerator is, it just matters what the denominator is. Right? So make sure the denominator is not 0. So if I solve this, I'm going to subtract 1 from both sides, and I get x can't equal -1, right? So we're just throwing out this number out of the domain of f, and we're just throwing this number out of the domain of g. So remember what happens when we throw a single value, right? If I were to graph that on the number line, we throw out a single value by putting back-to-back parentheses there. So the domain here in interval notation is negative infinity to 2/3 union 2/3 to infinity, right? It's all the numbers less than 2/3 and all the numbers greater than 2/3. So similarly here, okay, it's x can't equal -1. So all the numbers less than -1 work, all the numbers greater than -1 work, and so we're going to get negative infinity to -1 and -1 to infinity, right? That would be the domain, okay? So when we go and we talk about, well, what if we were to add these two functions together, okay, or subtract the two functions, or multiply the two functions, we're doing that A intersect B again, right? So where do these two functions overlap, right? Well, where they're going to overlap is everywhere but 2/3 and -1. Okay, so I'm not going to write this in interval notation. I'm just going to say x can't equal 2/3, comma, x can't equal -1. All right? It can't be either one of those numbers. Any other number was fine. All right? So you just kind of combine the two individual domains. Now, what about f divided by g? Remember, it's A intersect B, and g of x can't equal 0. Right? So you got to kind of look at the g function. When is g going to equal 0? Right? So if you can't see it right away, right, what would happen if I set g equal to 0 and solved? Right? It would give me my value. Right? So I'm going to multiply both sides by x plus 1. The x plus 1's cancel, and I get 4x equals 0. So if I divide both sides by 4, I'm going to get x equals 0. All right? So if I plug 0 into g, I'm going to get 0 over 1, which is 0. I can't let that happen. All right? We can't let g be 0. So this just gives us another number to throw out of our domain. So we would just say x can't equal 2/3, x can't equal -1, and x can't equal 0. Okay? So finding domains, big concept, all right? So not only did we find domains of square roots and fractions, we also are interested in domains of logarithms. So remember, in a logarithm, you can't take a log of 0 or a negative. So the argument inside here must be greater than 0. You can't let it equal 0. So just like with the square roots, with the radicals, where we took the radicand and set it greater than or equal to 0, what we're going to do here is just take the argument and set it greater than 0. And that's going to be our domain. So if I subtract 3 from both sides, I get x is greater than -3. Okay? So the domain here, greater than -3, would be -3 to infinity. Okay? Domains of functions, big concept. All right? All right, not much. Oh, yes, much. Okay. So let's do, let me stop this video because it's already at an hour, and I'll pick up this section on the next one.